So hello everybody. My intro is kind of interesting. I'm the CEO of terabyte, so we store information on thin ceramic layers and have explored this space in the last couple of years in building a product. And I tend to say I'm not the founder of terabyte, I'm the finder, and that relates to the Memory of Mankind project, which started off a couple of years saying, well, the most durable medium you can get is ceramics. Think of the cuneiform tablets. But how did I try to find this endeavor was quite interesting and has a lot to do with AI. 8 years back, I was fascinated seeing TPUs, GPUs having the first inroads into chess, into Go. And all of a sudden I thought, well, that's amazing. You know, no one thought that these things can learn so fast. And then I thought, I'm since 20 years in the mobile industry. Smartphones was trying to bring services around the globe. When is my smartphone smarter than me? I did a bit of calcs and came up like, okay, you need 100 petabytes per second processing power and probably 10 to 100 petabytes of storage. This is what you have in your brain with 20 watts. But then I soon realized the smartphone will not do it. Obviously, the network and the cloud will do it. And then you have a bifurcation. You have compute. Okay, this is what the GPUs do. But you have a need for massive amount of data storage. And that brings me actually to this question. So are we able as an industry to build enough memory and storage, fast enough memory and storage, to continue development beyond text-based ChatGPT kind of services? Think of an image. It takes much more compute. It takes much more storage. Think of videos. Think of 3D realities generated by AI. So I think this is going to be an interesting journey the next 20 years to, couple up every kind of storage and memory which we can. And I think this is quite interesting. Have seen the fast part today. Have seen Project Silica, kind of we're siblings in the way we do things. And I would like to explore with you our view on where the whole industry might go and what place terabyte may have. Now, terabyte stores only cold data. So once data is settled and permanent, very much like other approaches, we say, well, this is permanent. It's your memory. Think of it. I came from our brain. We want to keep our memories for a lifetime. So there are several areas. You understand it's very fast. It's becoming cold. You want to keep it for decades. Businesses want to keep it. Governments, scientific organizations. And then the question is, what is the impact of AI? And for that, we prepared a small, let's say, satirical video with some fundamental truth behind.
There have always been innovation leaps that have disrupted technical standards. For example, in the 1980s, data storage experienced a critical event. For the first time, we were gaining a complete picture of the Earth's surface. The Landsat satellites constantly transmitted images to ground stations where the data was recorded on tape. This took up a considerable portion of the then available storage space. The resulting severe shortage of magnetic tape was mitigated by overwriting of presumably unimportant or redundant data. As an unfortunate outcome, the only available high-resolution video recording of the Apollo 11 moon landing went lost. Today, we are at a similarly critical point. AI will permeate into every corner of IT. This will make our lives easier, increasing our productivity and enhance the multimedia experience. While accelerating processing performance for AI is an obvious prerequisite, there is another big challenge that is not broadly understood. AI will require and consume a lot of data storage space. AI needs huge amounts of training data, and assisting creative processes, it generates content at a record pace. And AI will make decisions, from IoT to autonomous cars, captainless cargo planes and vessels, to driverless trains and trucks. Imagine the first case in court involving personal injuries. where a company using AI cannot document how its AI algorithm derived the decisions that proved fatal. From that moment on, all AI decisions will be documented, either due to legal regulations or due to protective measures of companies, and stored for decades. The growth rate of production capacities of conventional data storage space will not be able to cope with this approaching data tsunami. Without an abundance of affordable storage space, we can forget about unleashing the full potential of AI.
Small satire, but pinch of truth, and it goes back to the very first appearance in media of AI, and that's what I like about it. Now, but get back to let's explore some use cases. So I come from the smartphone industry originally, so this was the obvious suspect. And you see a lot of services, personalization, enhance the cameras, etc. Finding whatever person you wanted to have find from your family. This is what the service is about. Now, it's about storing data. It's about soon 8 billion people storing data. And it's going to be for your lifetime. Or probably you start to inherit this data to your kids, right? Photographs, videos. Right. Then the car, definitely. We have 2.5 billion cars on the planet. If we all let them autonomous drive, we have a huge AI application. But we discussed it yesterday, how much terabyte is actually in a car and how much is replicated in the cloud, and these very even higher numbers than I bring up here. It's zettabytes, and it depends on how long we want to keep this data, how long are they relevant. Medical data, of course, again, it's a lifetime case, okay? Because you have some x-rays, you have some other stuff going on, and 8.5 billion people. In the 30s, we're going to incur a lot of data, which we store for a lifetime. Exploration of oil, a very strong use case, a lot of parts of the GDP, and you can improve the finding of future resources of oil and gas by using AI. Financial industry, while this is very clear that you want to have trading algorithms based on AI, risk management, and so on and so forth, it's also a huge part of our economy, 8% of global GDP. 10% of these revenues go into the IT. And then finally, big science. And it's always interesting to hear if you talk with big science organizations, they say, well, we want to store the data forever because they are so valuable and very expensive to create. And then if you ask on what medium they store it, then it's on tape. So kind of a contradiction. And then finally, and this brings me back to the starting point of the discussion, entertainment industry, 2.5% of global GDP, and 80% is digital. And soon a lot of stuff will be generated with AI, and it's then not only images, it's videos and whatever we're going to see in future. So it takes a lot of resources. Now, let's go a bit more into data. There's public data on, how the last 10, 15 years showed how a superhuman qualification came in reading, recognition, and so on and so forth. And I mean, the last 2 years with ChatGPT were clear. This is an amazing revolution going on. But it also correlates to compute. In the past, we had always, every 2 years, we double the speed of our processing. Now it's in a few months. I think at a certain time it was down to 2 months of doubling the compute. Yeah. And if you want to do compute in the traditional way, we have it lined out here, the CPUs, they were also growing with the same speed. And at a certain time, we had also 2x every 2 years on the storage. So everything was fine. Now comes a change in paradigm. We start to use GPUs, and not only that, we put them in clusters. So the growth of the compute of individual racks is skyrocketing. And we don't have really a matching medium which can scale at that speed. So it will end up in massive production increase, or we find other medium, or other media, because I think it's going to be a general industry approach. We need something new. We need something which kind of can cope with this massive growth of compute and data storage required, so a new S-curve. And then, of course, there are other limitations out there. We know AI is power hungry. It's not about the 20 watt our brain requires. It's much more. And so we have seen, we are now in a phase where AI providers start to think about nuclear energy co-located to their AI clusters because they are so power hungry and you don't want to screw the planet at the same time. I think over time this will be solved by less power hungry chipsets, so smaller process size will lead to lower power consumption. And then probably towards the end of the decade, this is where I think memory and storage might become the bottleneck. And this is the hypothesis I like to discuss with you. If we look a bit back historically, this is not surprising. We had been every 30 years, 1,000 times more installed base. And it's easy with the coming of AI that probably this trend will continue the next 20 years. Now, if we break it down for the next 20 years, it's 10 times the storage every 10 years. So we would need 100 times the storage density if we want to keep the same volume and space. We need to have it 100 times more energy efficient. And of course, the cost need to go down, let's say $1 per petabyte per month or something. Today, you can't imagine that this is going to be that kind of price point. But if you think of the budgets for IT and storage will not grow, right? So, and we have this on blast, on performance, and storage needs. So something has to be done. And so if you put this together, all this trajectory, for sure we're going to have a lot of SSDs, hard drive, and tape. There might be something like emerging technologies. So the gentleman from Microsoft Silica is very much in this league. We hear tomorrow, I think, about DNA storage as one of the options. But I want also to emphasize about the latencies. I think what's missing in this evolution, there is microseconds access to SSDs, milliseconds, hard drives, and tape is fairly slow because you have tape. And something in between, so in the range of a couple of seconds, probably this is sought for, and it should be very cost efficient. Otherwise, we don't fulfill the budget requirement we just exclamated. Now, this is about the prototype we built, and it cost a lot of attention, which I'll tell you in a minute.
Within a shortest period of time, we evolved our initial proof of concept into a fully operational terabyte end-to-end demo system, which consists of one write-read rack and several library racks. Terabyte uses thin glass with a dark ceramic layer as data storage media that are stored in cartridges in a robotic library. To write the data carrier, a cartridge is transported from a library rack to the write-read rack. Next, it is opened and a data carrier removed and positioned on a stage. Data is written by QR code-like patterns using a femtosecond laser pulse that is shaped by a digital micromirror device and projected through microscope optics onto the surface of the data carrier, ablating holes or no holes into the ceramic layer, representing zeros and ones. During the forward movement of the stage, a line of QR patterns is written, which are read back and verified during the backwards movement by a microscope camera. When a data carrier is fully written, it is returned into the cartridge, which is then moved back to the library. The read workflow is similar, whereby only the microscope camera is engaged and data is read in both directions of the stage movement. Error correction and file allocation will work similar to other mainstream data storage technologies. We used only commercial off-the-shelf components to build the demo system, delivering impressive progress in a short time, with a small team and limited resources. While providing an end-to-end workflow demonstration, this first system obviously doesn't compete with today's state-of-the-art storage systems. Terabyte's roadmap will enable us to reach leading-edge data storage technology specs. With the footprint of data center racks, Terabyte has the potential to become the future standard for sustainable long-term data storage. The simplicity of Terabyte's data carrier is only one of many reasons why Terabyte is a cost-effective and easily, as well as fast, scalable technology for future data storage. No energy is consumed to retain data, and no data migration is required once written. Or to be more precise, only one data migration is needed. Your last one onto Terabyte.
So this prototype caused a lot of attention in the press. One of the results was we are working now with CERN on experimenting how we can best store their data. So it's the collider in Europe. Pure Storage invested in us. Sounds like a strange idea, but very complementary if you think. We are absolutely not in rewritable, we are just permanent. And just lately we were happy to announce that Stephen Campbell, former CTO of Western Digital and Hitachi Global Storage, joined us as CTO because this is a prototype and we are well aware that the next stage is going to be building a product for an archival case, not at the storage density we would wished for, but we are on a way, which I'm going to show you in a second. Now, what is the technology in it? What is also like the similarity, but also the difference to Project Silica? We use very thin substrates and we coat them with ceramics on both sides. And we stack them in total in a quadrich, as you have seen. So somewhat from the type of laser, it's the same thing. It's the same material class like silica. The writing mechanism you have been seeing is quite different. I come to that in a second. Now, if you see it, these glasses, we just use matrix codes, one layer, basically two layer, both sides. Why can't we stack them? Easy question. Difficult to answer how we can really make it. Very simple. The ceramics you use is harder than steel, so you don't have to fear scratches. So this is a kind of a paradigm change, and it allows also random access. I think this is where we come up in the seconds of access time. And it's a physical storage of information. Now, to summarize the system, you have seen this robotics. Why did we choose not a fancy new robotics? Very simple. We didn't have the money, but also we didn't have the need. Taking a consensus in the industry on tape mechanization and have this produced at large scale is easy if you have partners who can do that for you. We don't really want to explore that. Then you have, on the one hand, the cartridges I mentioned with this thin ceramics. You have this parallel writing process and reading process. This makes a huge difference in terms of writing performance. Because different than a disk where you have one beam and a rotating disk, here we just blast 2 million bits in one shot at high rep rate. Reading is also simple. It's an optic medium, so over several generations you can read it as long as you know how to decipher it. Random access was mentioned, stacking the glass, and of course we want to provide this with a simple interface for now. We'll see what the future will bring in terms of interfaces. This is a bit of like our roadmap. We start with this pilot system as mentioned for CERN and grow on data capacity, on speed and access times going down to reach this second kind of access time. And the several markets we address initially and start soon with it is archiving, it's sort of infrastructure OEMs, that's Pure, and others may join this endeavor as complementing to their system. And then finally, cloud service providers. Definitely the most challenging customer group. Now, if we position ourselves between tape and hard drives, we left out the SSDs because for cold they are not really relevant. You see, well, of course, we have some advantages when it comes to longevity, energy consumption, etc. But if you separate the medium and the write read, of course, you have a couple of seconds for accessing the data. So that's basically it. But you have other massive benefits for the future. It can be easily situated in a standard data center. Temperature swings are not a problem as with other media like tape. It's saving a lot of energy versus hard drive. And the TCO analysis we did together with hyperscalers indicate at scale production. And think of it, thin glass is produced in huge quantities because everybody wants to have large display screens. So this brings the cost down significantly more than we expected last year. So we expect it to go down like 95% versus hard drive. This is summarizing this, and then, of course, we said, well, what should the data storage of the future look like? If we don't want to screw our budgets, we have to get the cost curve down, all the way, because otherwise we're going to screw up the storage budget, or we start not to store. So we have a gap. And the main reason is the medium is low cost, because you produce it already in huge quantities, so we leverage this industry. You don't replace it that frequent. So because the medium could last hundreds of years, we probably don't do that. You do this probably every 15 years or something. It's more reasonable to assume that in our cases. And then no data migration, no climatization, because glass is in a wide range of temperatures, has no bit rot or whatever. The other aspect is CO2 emissions. So once written, very similar like tape. You don't need energy. You only need energy to access it. On the other hand, it's only glass. It's not a fancy stuff. It's glass with 10 nanometers of coating, which is about 0.01% of the whole volume. So it's easy to recycle. And we did an analysis last year. We were not able to provide that, but now we built up a model on modeling this volume of the various media types on installed base and in respect to shipments. And the OPEX, that means like when I run a system, it consumes all the time energy and CO2, so we call it CO2 OPEX. And then we have the CapEx. This is when you build the device, you have an embedded burden on CO2 emissions. And if you combine this to a model, you basically end up saving quite a lot of megatons of CO2 on a global scale, provided this emerging technology, I count here silica as well as us as DNA, could have a good contribution to that, and basically you're going to have peak CO2 for data storage probably sometime early in the 30s. It accounts, on the one hand, there are two studies behind, and I referenced also the links to it. There is one from the US and Canada looking at the SSD and hard drive, what they consume, and interesting enough, the embedded CO2 in SSDs is pretty high. And then there is another study from Germany looking into data centers and how is the breakdown of energy consumption along the whole stack. So because you have to operate in cool data centers as well. So we modeled this into that simulation. Now, another observation so far, we always talked about, the storage pyramid, a very old paradigm. And here again, a kind of bit of a satire coming up. We have now all these use cases. You have retention, and aligned with this, you have latency and this type of media. And we think it might, with the AI, change into a completely different shape, more like a barbell. Why? Because we want to keep a lot of data hot to do the inferencing or whatever we want to do with the AI workloads. And there's, on the other hand, huge amounts of data. Think about the car data for training your autonomous driving. But you want to keep it for 30 years because you develop 5 years the autonomous driving, you have 10 times production, and you have 15 times of the last car in service. So in total, there is a bit chunk of data. And this is where we think a second access, new technology, might make a lot of sense. And this is like the call for action for all of us to think about these type of technologies. There has been a third-party assessment from the National Academy of Science earlier this year. And it was a clear statement. It was actually done for the intelligence community, where they said they have exabytes of data which they want to preserve for long, 25 to 50 years. And obviously SSDs and hard drives and tape didn't qualify for that because they have to be replaced. So they were looking for new technologies, and terabyte and silica came out as the one which are on a prototype level, on the brink to productization. We might have a bit of an advantage when it goes to transferring the technology to a first sort of simple product for archives, think about governmental archives. Then silica, we share the same concern on getting the capacity for femtosecond lasers up, because this is like really the bottleneck at the moment. And then there's, of course, DNA storage. We're going to hear tomorrow, I think, as well. Some people, biomemory and others, talking about that, definitely having a place in this huge growing part. But it looks like National Academy considered this as TRL4. I hope you're familiar with the TRL concept, technical readiness level. 50 years back was, or 60 years back was introduced by NASA. So 6 is like prototype, 9 would be a product. So this is where the challenge starts and where we try to get this one product. Now, last year I showed this kind of slide because obviously you have to think a bit about 20 years, right? So how can we increase the storage density? And with every optical medium you have a limitation, wavelength, right? So we think we can get to 100 petabyte per rec till the end of the decade, but then you end up in limitations on the process size or spot size or bit size, whatever you want to call it. And we had been able, and giving a glimpse of what we can do with particle beams. Remember, particle beams are an ion moved in an electric field, bombarding on the surface and writing a pattern. And we also were hypothesizing about helium-ion beam and electron beam. And this is what we've got as a result. We explored in the past the femtoseconds. You see the pixel size, you see the data capacity. Go beyond the laser, go to particle beams. 30 nanometers would be 1 terabyte of one surface on a 10 by 10 centimeter sheet. And this is like 4 or 5 weeks old. It's a first glimpse of how small you can get. It's not a matrix, it's just a few dots. But with electron beams, you can write 1.5 nanometers. So if you really bring this to a product in 10, 15 years, you would have insane storage densities. That brings the cost down as projected. Having said that, this is a proof of concept study. It's not yet the product, and a lot of investment has to go into it. But we want to leverage the semiconductor industry because electron beams are on the forefront of miniaturization. So I think we are in good company here and support. Oops. Was too fast. So I have been alluding on we need to do more research. So while we productize the simple femtosecond stuff, we are working with several European institutions, hope to make contact also here in the US, to make this a wider approach, where we say, well, there needs to be innovative coatings for this kind of ceramic storage. And we start off with experimenting with fluorescent material. They're easier to read. We start off with magnetic material. They're easier to write with E-beam. We are now exploring the UV much more in this context, together with Fraunhofer, well-known institution in Germany, and multi-layer kind of coating, overlapping matrix, very similar to shingled magnetic recording, only in the optical realm. And then helium-ion beams, there has been already some good results we have been seeing, and then of course our own results. But this is like about 10 people as a research organization, governmentally funded, and happy to explore with you. And science organization also present here, how we could evolve. In Europe, we have the Technical University of Vienna. We have CERN, we have IMEC, the semiconductor guys from Leuven, and Helmholtz helping us on this fundamental research. It's going to reach out 10, 15 years. And then in the US, I mentioned Pure Storage, the founder of Pure Storage, John Colgrove, is on our board helping us to get from this European sort of roots to a more like a company which can establish itself here in the US. University of Santa Cruz University of Boulder. And what do we need from this community? Basically, it would be great to investigate what the storage stack's going to look like, how we integrate into what we have here before, on the hardware side, on the software side, and happy to discuss afterwards over lunch. And I almost made it till 12. Thank you.
So Christian, we have time for a few questions because you actually finished before on time.
Oh,
so
I'm before on time, wow.
Yes, I'm coming over to you.
Hendrik from MLE. Where do you anticipate will be in the terms of cost for a writer, and in terms of cost for a reader, and in terms of cost for a media?
We always do this in TCO terms because it's very difficult in a certain point in time to say what it's going to cost. So we did this intense analysis, taking industry learning curves into account for all the elements. And we think we can bring the CapEx down to $1 per terabyte. And hence we come to this very low TCO models. So overall, more I can't communicate right now.
The question is, given that we are storing it in the library, how are we indexing into specific data that you would need?
Could you repeat, sorry?
Given that we are storing the dry disks, the ceramic disk in the library, right? How do we index into specific data if you need it?
At the moment, we offer only S3 interface, so it's bulk storage. And this is also probably a part of the discussion we are having. And there's a lot of work to be done on, how sharding the data and making sure that when one of the modules is not available, how do you make sure you get it in time? So a lot of work has to be done on that. But it's randomly accessible. It's more like the software layer. And as you know, Europeans are probably not particularly good in doing software layers. We're good in the hard stuff. And looking for your support in that field.
Any other questions? Okay, well,
Very good,
thank you
Dan.
very much. All
Thank
right.
you.
Lunchtime. Woo!